Hello, I'm Carlos Rosso, and this is the CRS channel. We're going to continue on with physics problems in kinematics, and we're going to follow on to problem 10. Okay, in problem 10, we have a body, falling body, and we're assuming that the effective air resistance is present and acting on the falling body, and that we can use the following expression for the acceleration of the body, which can be written in the following way: A equals dv dt equals minus g minus kv, which is the acceleration of gravity, which is 9.8 meters per second squared. K is a constant, and so given this expression for the acceleration, then we must derive a formula for the velocity of the body, the falling body, as a function of time, assuming it starts from rest, that is, v sub 0 equals 0 at t equals 0. We are to determine also an expression for the terminal velocity, which is the maximum value the velocity reaches. Now, additional to this, we will also obtain an expression for the position of the body. Okay, so to obtain the velocity, we know that A equals minus g minus kv, A equals dv dt, so that dv dt equals minus g minus kv, which is what we had here. And we take this dt, send it over here, and take this minus g minus kv and send it over here as the denominator, and we have dv over minus g minus kv equals dt. So to obtain the velocity, we integrate on both sides. Here we integrate from v0 to v. Here we integrate from 0 to t. So by making a certain change of variables, we name this new variable u, and u equals minus g minus kv, so that du equals minus k dv. So that means that dv equals minus du over k, which is what we have here. So we replace dv with minus du over k, and here this is u. So this expression changes to this one, and we still have the dt and the integral is to be evaluated between these two integration limits for time, and this integral for u is to be evaluated between these two integration limits, minus g minus k v0, and here we have minus g minus kv. So we take this minus k out of the integral, and we are left with du over u. The integral of du over u is the natural logarithm here, a missing term. which is u. So this is natural logarithm of u to be evaluated from minus g minus kv0 to minus g minus kv. So that leaves us with this expression here, minus 1 over k times the natural logarithm of g plus kv over g plus kv0. And that is equal to t. So we send this minus k to multiply here. And we're left with the natural logarithm of j plus kv over g plus kv0 equals minus kt, equaling minus kt. So we evaluate the exponential on both sides. So we're left with g plus kv equals g plus kv0 after sending this over to multiply to the right side times minus e to the minus kt, or exponential of minus kt. Okay, so sending the minus g here, the g to the right side, so it'll change sign, and sending this k to divide, we are left with this expression here. Now we can check things out by putting t by equaling t to 0 here, and we obtain that for t equals 0, we are left with minus g over k plus 1 over k times g plus kv0. In which case, if I make v sub 0 equal to 0, all these two terms cancel out. Another way of looking at it is making v sub 0 directly equal to 0, which leaves me with this expression here, which would be the general term vt, or v of t, equals minus g over k times 1 minus e to the minus kt, or exponential of minus kt. Now, the terminal velocity would then be equal to v equals minus g over k, which is the case in which I assume that this term here, as t tends to infinity, then this term tends to 0, and I'm left with just this. So this would be the maximum value for v of t. Well, g over k would be the maximum value for v of t. The minus sign refers to the fact, or makes reference to the fact, that the body is falling. So the velocity is in the negative direction. Okay, we're going to continue with, we can continue. Okay, so at the terminal velocity, we also have then that a would be 0. That means the acceleration turns to 0. As the since the body starts from rest, its minimum value, the minimum value in terms of absolute value or magnitude, minimum speed would be 0, and of course the maximum speed would have to be g over k for which then I would have that the acceleration would be 0, which you can see if you replace minus g over k here. K and k go cancel out, the minus cancels out with this minus, leaving a plus, and minus g plus g equals 0. So as t tends to infinity, v tends to minus g over k, and a tends to 0. Okay, now let's see how we can do to obtain the position of the body, of the falling body. We have that v equals dy dt, and therefore we have the integral of dy from y evaluated from y0 to y will be equal to the integral of v dt to be evaluated from 0 to t. So the formula for the velocity that we're to use here is this one. So we replace this expression within this expression here, and we get this expression here. Okay, so the integral of this is t, which is this. The integral of dy is y, evaluated from y0 to y, is y minus, gives us y minus y0. The integral of e, of the exponential of minus kt, is minus 1 over k exponential minus kt, to be evaluated from 0 to t, gives us this expression here. Exponential minus kt minus 1. Okay, we're going to finish up with this problem 10 in the next video.